What's going on, guys? In this video we're going to be covering different models we can use when we have a count dependent variable. The model we're going to be covering the most is going to be our Poisson regression. So I'm going to give the derivation for its log likelihood now. So if we start off with just the likelihood, it's going to be equal to the product of I is equal to 1 to n of, and then just our PMF for a Poisson distribution, or e to the negative lambda times lambda to the y over y factorial. Now we want to choose a value of lambda that ultimately maximizes this equation. But the problem with this is on the right side, these values are going to form probabilities, which means the values are going to be between 0 and 1. So as we add more and more numbers, this value is going to get smaller and smaller and smaller. And ultimately this is going to lead to an overflow error. So in order to counter this, we want to make this additive. So we can do that by taking the log likelihood. So if we take the log of both sides, our formula is now going to be the summation, or additive. And our formula is going to be yi times the log of lambda minus the log of y factorial. And the rules we use to achieve this is the log of e to the negative lambda is equal to negative lambda. The log of lambda to the y is equal to y log lambda. And if we take the log of a fraction, such as x over y, it's going to be equal to the log of x minus the log of y. So by applying these rules, we can get from this formula to this formula. Now the function that we're going to be inserting into for our lambda is going to be e to the z, where z is going to represent our beta 0 plus beta 1 x1. Now the reason we use e to the z for a Poisson distribution is that no matter what value you enter into z, so from negative infinity to positive infinity, you're going to end up with a number between 0 and infinity, which is what values a count variable can take, any value from 0 to infinity. So since the function we entered in is e to the z, so our lambda is equal to e to the z, then our link function is going to be the log of lambda is equal to z. So this is our link function. So we're going to choose values for our parameter estimates that ultimately maximize this equation, or our log likelihood. So now let's do an example. Say we ran this model using Poisson distribution where we had one predictor x and the dependent variable y was a count variable. And the parameter estimates we got were negative 0.2 plus 0.49x. So in order to find our predicted values, we would enter them into our formula of e to the negative 0.2 plus 0.49 and then times x. So for our first observation, the x value is 1, and this will produce a value of 1.34. So this would be our prediction. And for our second observation, we do the same thing, so e to the negative 0.2 plus 0.49 and then times our x, which is 3, would produce 3.56. For a third observation, we have an x value of 2, which would produce 2.18. And then finally, for our fourth observation, we'd have e to the negative 0.2 plus 0.49 times 4, which would give us 5.81. So these would be our predicted values. So now let's find our Poisson residuals. So the formula we're going to use for our Poisson residuals is going to be our observed value minus our predicted value, and then over the square root of our predicted value. So you always want to use for your Poisson residual, the denominator is going to be the standard deviation from your distribution. So since we're using a Poisson distribution where the predicted value is equal to lambda and our variance is equal to lambda, then the standard deviation is equal to our square root of lambda. So for our first Poisson residual, our observed value was y is equal to 1, and then our predicted value was 1.34. And then we just divide this value by the square root of our predicted value, or 1.34, and this will produce a value of negative 0.29. So our first Poisson residual is negative 0.29. Then for our second observation, our y value was 3, we predicted a value of 3.56 divided by the square root of 3.56, and we will get negative 0.3. For a third observation, our y value was 3, minus our predicted value of 2.18, and then over the square root of 2.18, which will give us 0.56. And then finally, our observed value was 6, minus our predicted value of 5.81, over the square root of 5.81, and we'll get a value of 0.08. So with these 4 Poisson residuals now, we can get our Poisson chi-square statistic, which is just the sum of square values from our Poisson residuals. So for our first residual is negative 0.29. So we're going to square that value, add it to our next residual squared, or negative 0.3, and then 0.56 squared plus 0.08 squared, and adding these together we will get 0.494. So this is going to be equal to our Poisson chi-square statistic. So then, since this measured residuals, the smaller the value, the better. Now we can move on to deviance, where the formula is going to be equal to 2 times the maximized log likelihood of our saturated model minus the maximized log likelihood of our current model. And here we have the formula for our maximized log likelihood for our Poisson distribution. So wherever we see this function, or lambda z, is where we're going to enter into our predicted value. So for our saturated model, we're always going to predict the current observation, since the saturated model predicts perfectly. So our formula is going to become yi times the log, and then our current observation, minus our current observation, and minus the log of y factorial. So this is going to represent our saturated portion. And then this is going to be minus yi times the log. And now since we're using our current model, we're going to use our predicted values from our current model, or y hat, minus our predicted value, minus the log of y factorial. And then if we were to sum these values up over each observation and multiply it by 2, this will give us our deviance value. This is current model. Now we can simplify this equation to instead be 2 times the summation of yi times the log of yi minus the log of our predicted value minus yi plus our predicted value. Now let's do an example. Where on the left we have our observed value and we have our predicted value. So if we were to plug it into our deviance formula, for our first observation we would get 2 times 3 times the log of 3 minus the log of 4 minus 3 plus 4, and this will give us a value of 0.274. So we can say our first deviance residual, or deviance residual for observation 1, is 0.274. For our second observation, we would get 2 times 4 times the log of 4 minus the log of 3 minus 4 plus 3, and we'll get a deviance residual equal to 0.301. And then for our third observation, we'd get 2 times 3 times the log of 3 minus the log of 5 minus 3 plus 5. And this will give a value of 0.94. So now if we sum up these three values, or 0.274 plus 0.301 plus 0.94, we'll get a deviance of 1.515. Now, instead of solving, here we solved each observation independently, where we took our saturated model from that observation minus the current model for that observation. Now instead, you could also just find your saturated model independently and your current model independently, and then at the end subtract the two and multiply by 2. Poisson regression with exposures. So let's say you had 3 classes, math, science, and history, and you were trying to decide which one was the easiest based off the number of A's that they gave out. So by looking at this information alone, you would say that history is probably the easiest because they got the most A's, and math's probably the hardest because I got the least amount of A's. But let's say we add an extra variable now, which is the number of students. So let's say the number of students that took math was only 10, the number of students that took science was 20, and the number of students that took history was 30. So now you can see that history was actually probably the hardest class because only 1/3 of the students got A's. Meanwhile in math, a half of the students got A's. So what we're essentially doing is we're saying the number of A's per student now instead of just A's, and this is going to be equal to, and again our same function for a Poisson distribution, or e to the beta 0 plus beta 1 x1. So now if we want to find the link function of this, we take the log of both sides. So our log of A's over student is going to be equal to our beta 0 plus beta 1 x1, and this is the same thing as the log of A's minus the log of student is equal to our beta 0 plus beta 1 x1. And finally, this is equal to the log of A's is equal to our beta 0 plus beta 1 x1 plus the log of student. So this log of student here is going to be known as our offset. And this is going to be our new link function. So the output produced by this, it's no longer going to be the number of A's produced in a classroom. Instead, it's going to be the number of A's per student for each subject. So by adding these exposures, ultimately we're changing our dependent variable from a count to a proportion, where it's no longer just number of A's, it's A's per student. And this is our link function. So thus far we've only been focused on Poisson regression, but there's a major problem with Poisson regression, which is this assumption it makes that the mean is equal to the variance. So what do we do when this doesn't hold? So certain models we can use when this doesn't hold, or we'll start when the variance is greater than the mean. We can use the negative binomial model, the zero-inflated model, the hurdle model, or the heterogeneity model. And when this variance is greater than mean, this is also known as over dispersion. Now, when the variance is less than the mean, we can use our hurdle model again. So notice hurdle model you can use when variance is greater than the mean or less than the mean. These other four models you can only use when the variance is greater than the mean. And when the variance is less than the mean, this is also known as under dispersion. So over dispersion, the data is dispersed or more spread out than the mean. Under dispersion, it's less spread out than the mean. Now, for a negative binomial, the only thing you really have to know about this model is it's a more flexible version of the Poisson. And it uses 2 parameters instead of 1. And for a heterogeneity model, it models the response as a continuous mixture instead of a discrete distribution. For the other two models, Zero-Inflated and the hurdle model, we're going to solve two different examples to show how those models work. Zero-Inflated model. So you want to use this model when you have an abnormally large number of zeros. So the example used in the book of when you could use this is to model claim counts, where you might ultimately have a group of people that had a claim but chose not to submit it because they're worried about their rates increasing. So we can show those here over on the right in red, where they had a claim but they didn't submit it. So a zero-inflated model is actually made up of two different models. So the first model is going to be a binary model, where the probability that y is equal to 1 represents that you had a claim but you chose not to submit it. And then our second model is going to be our count model, which is just going to represent the count of claims. So the different models we can use for a binary portion, we could use either logistic regression or probit regression. And for our count, we generally use either Poisson or negative binomial. Now if we wanted to form our PMF from these two models, or the probability that it would come out to said observation, then for the probability that the count is going to be equal to 0 is going to be equal to our pi, or the probability that y is equal to 1, which means we had a claim but didn't submit, so that's everything here in the red, and then plus 1 minus our pi, which means that we had a claim and we submitted it, but it just happened to be 0. So that's just going to be equal to our function evaluated at 0, or our count at 0. So this is going to be when j is equal to 0, or our count is equal to 0. Now when our count's not equal to 0, it means we had a claim and we filed it, or 1 minus pi, and then just our function at that value. So when j is not equal to 0. So let's say we had a pi value equal to 0.1. So this would mean 1/10 of people had a claim but they chose not to submit it. So that means 0.9 or 90% of people submitted a claim. So that represents this whole portion right here is 90%. So then we're just using it just like we would a regular count distribution or a regular Poisson distribution, except for multiplying whatever value we get by 0.9. So evaluated at 0 times 0.9 would just be this value right here. And then for the rest, so let's say counts equal to 1, 2, 3, 4, 5, it's just going to be whatever the probability of that is from our count distribution, and then times our remaining population, which is just going to be 0.9. So now let's do an example. So let's say we ran a zero-inflated model where we used logistic regression to measure whether or not we had a claim and chose not to submit it, and we used Poisson regression to measure the number of claim counts. So with logistic regression, the parameter estimates we got was 2.66 minus 0.84x. So if we wanted to estimate our pi value, or the probability that we had a claim but chose not to submit it, at x is equal to 5, we're going to enter these values into our sigmoid function, which is 1 over 1 plus e to the negative z. So if we enter that into our equation, we're going to get e to the negative 2.66 minus 0.84 times 5. And this will produce a value of 0.18. So we can say that 18% of people had a claim, but they chose not to submit it. So now we can move on to our Poisson distribution to measure the count. So for Poisson, the function we used was e to the z. So if we plug that into our formula, e to the negative 1.23 plus 0.34 times 5, and we'll get a lambda value equal to 1.6. So now from this information, we can find the probability that we're going to get a different number of claim counts when x is equal to 5. So for instance, the probability of 0 claim counts is going to be equal to, and this is the formula we're going to be using. So 0 claim counts is going to be pi, or the probability that we had a claim but didn't submit it, so 0.18, and then plus 0.82 times, and now the function that we're going to use is Poisson with a lambda of 1.6. So if you remember, for Poisson distribution, the probability of 0 is equal to e to the negative lambda. The probability of 1 is equal to e to the negative lambda times lambda. The probability of 2 is equal to e to the negative lambda times lambda squared over 2 factorial, and so on, so on, so on. So for the probability of 0, it's just going to be e to the negative lambda, or e to the negative 1.6, and this will produce a value of 0.35. So we can say there's a 0.35 chance that we're going to have 0 claims when x is equal to 5. Now we can do the same thing with the probability that we're going to get 1 claim, which is going to be equal to 1 minus pi times our count function. So 1 minus our 0.18 times our count function, which is going to be e to the negative 1.6 times 1.6 for the probability of 1, which will give a value of 0.26. And then if we want to find the probability of 2 claims, it would just be 1 minus 0.18 times e to the negative 1.6 times 1.6 squared over 2 factorial, which will give a value of 0.21. And then you can do this on and on and on and on. Hurdle model. So just like our zero-inflated model, we're going to use our hurdle model when we have an absorbent amount of zeros. And again, our hurdle model, just like our zero-inflated model, is going to be broken down into 2 different models: a binary model and our count model. But this time, our binary model, for the probability that y is equal to 1, is going to represent the probability of not overcoming our hurdle. So for instance, say you went to a pool and you wanted to count the number of laps that people did. Well, if they didn't enter the pool yet, then they did 0 laps. But given that they entered the pool, they did at least 1 lap. So the PMF for our hurdle is going to be, when our j is equal to 0, it's just going to be equal to our pi. Or if they didn't enter the pool yet, so they did 0 laps. Now, given that they entered the pool, then they must have done at least 1 lap. So it's going to be 1 minus pi times our count function at that value over 1 minus our count at 0. Now, this part of the function stems from a truncated distribution, where we can say the probability that y is equal to y, given that y is greater than 0, is equal to the probability that y is equal to y over the probability that y is greater than 0, which is equal to the probability that y is equal to y over 1 minus the probability that y is equal to 0. Now an example. Say we ran a hurdle model where we used logistic regression and we used Poisson regression. So for a logistic regression, the parameter estimates we got were 3.43 minus 0.8x. And for a Poisson regression, the parameter estimates we got was negative 1.18 plus 0.33x. So if we wanted to find our pi, or the probability of not overcoming the hurdle, which in our case they didn't enter the pool yet, we'd enter it into our sigmoid function, 1 over 1 plus e to the negative z. So 1 over 1 plus e to the negative 3.43 minus 0.8, and we're using x is equal to 5, and we get a pi value equal to 0.36. And then to find our lambda value, the function we use for Poisson is e to the z. So e to the negative 1.18 plus 0.33 times 5, and we'll get a lambda value equal to 1.6. So if we want to find the probability that our count is going to be equal to 0, using these formulas, we just have to plug in our value of pi. So the probability that count's equal to 0, or they didn't enter the pool yet, is just 0.36. Now the probability that count is equal to 1 is going to be 1 minus 0.36, and then times our function evaluated at that value divided by 1 minus that function evaluated at 0. So evaluated at that value is going to be our e to the negative 1.6 times 1.6, because it's just our Poisson distribution, the probability that y is equal to 1, and then divided by e, or 1 minus e to the negative 1.6. And this will produce a value of 0.26. And then we can do one more example, the probability that count is equal to 2. And it's going to be 1 minus 0.36 times, and then our lambda distribution, our Poisson distribution at 2, or e to the negative 1.6 times 1.6 squared over 2 factorial, and then divided by 1 minus our probability is 0, so 1 minus e to the negative 1.6. And this will produce a probability of 0.21. So that's going to wrap up this section. I hope you enjoyed, and I'll see y'all next time. Thanks.